Welcome to MathGPT. Today, we're going to explore standing electromagnetic waves. When electromagnetic waves reflect off a perfect conductor, they create a fascinating pattern called a standing wave. Before we dive into standing waves, let's first understand what a regular traveling electromagnetic wave looks like. An electromagnetic wave consists of oscillating electric and magnetic fields that are perpendicular to each other and to the direction of propagation. The electric field, which we'll show in pink, oscillates in one direction, while the magnetic field, which we'll show in blue, oscillates perpendicular to it. These fields propagate through space at the speed of light, carrying energy as they go. Now, let's see what happens when an electromagnetic wave encounters a perfect conductor. When the wave hits the conductor, it gets reflected. Due to boundary conditions at the surface of the conductor, the reflected electric field is 180 degrees out of phase with the incident field, while the magnetic field remains in phase. The superposition of the incident and reflected waves creates what we call a standing electromagnetic wave. In a standing wave, there are certain points called nodes where the field is always zero, and other points called antinodes where the field reaches its maximum amplitude. Importantly, the electric and magnetic field components have their nodes and antinodes at different positions. Where the electric field has a node, the magnetic field has an antinode, and vice versa. Let's look at the mathematics behind these standing electromagnetic waves. For an electromagnetic wave traveling in the positive x direction and reflecting off a perfect conductor at x equals 0, we have incident and reflected waves. The incident electric field is represented as E incident equals E naught sine of kx minus omega t. The reflected electric field is E reflected equals negative E naught sine of kx plus omega t. Note the negative sign, representing the 180-degree phase shift upon reflection. When we add these waves, we get the standing electric field. E standing equals E incident plus E reflected equals E naught sine of kx minus omega t minus E naught sine of kx plus omega t equals negative 2 E naught sine of kx times cosine of omega t. This gives us the important spatial dependence of sine kx, which is why the electric field has nodes at kx equals 0, pi, 2 pi, and so on. Similarly, the standing magnetic field has the form of B standing equals 2 B naught cosine of kx times sine of omega t. With the spatial dependence of cosine kx, the magnetic field has nodes where kx equals pi over 2, 3 pi over 2, 5 pi over 2, and so on. Notice that where the electric field has a node, the magnetic field has an antinode, and vice versa. This is a key feature of standing electromagnetic waves. Let's visualize the standing electromagnetic wave in a more three-dimensional view. Here we have the perfect conductor in the YZ plane at x equals 0. The electric field oscillates along the y-axis, and the magnetic field oscillates along the z-axis. Both fields vary with position along the x-axis. Notice how the electric and magnetic fields are 90 degrees out of phase in time. When the electric field reaches its maximum, the magnetic field is 0, and vice versa. This time dependence, combined with the spatial distribution we discussed before, creates the complete standing electromagnetic wave pattern. Standing electromagnetic waves have numerous important applications in modern technology. For example, they form the basis of microwave cavities used in microwave ovens and particle accelerators. In these cavities, the electromagnetic wave bounces back and forth, creating standing wave patterns. These waves are also crucial in the operation of lasers, where light reflects between mirrors to create standing wave patterns. Another application is in waveguides and transmission lines, where standing waves can form when there is an impedance mismatch. To summarize what we've learned, 1. Standing electromagnetic waves form when an EM wave reflects off a perfect conductor. 2. The electric field has nodes at positions where kx equals 0, pi, 2 pi, and so on, which corresponds to multiples of half wavelength from the conductor. 3. The magnetic field has nodes at positions where kx equals pi over 2, 3 pi over 2, and so on, which are offset by a quarter wavelength from the electric field nodes. 4. At any given point, the electric and magnetic fields oscillate 90 degrees out of phase in time. Understanding these standing electromagnetic waves is essential for many areas of physics and engineering, from antenna design to quantum mechanics. Thank you for watching this explanation of standing electromagnetic waves. This phenomenon forms the foundation for many fascinating areas of physics and engineering. Remember that when waves reflect off a surface, they can create these stable patterns that behave quite differently from traveling waves. If you're interested in learning more, you might want to explore topics like resonant cavities, waveguides, or even quantum field theory, where similar mathematical principles apply.